So good morning to all of you. And first of all, I thank OP Jindal University for inviting me for such a presentation. So I'm thanking all the organizers, and very good morning to all the attendees and all the people around here. So I have been working in process modeling more than maybe 23, 24 years by now. So it has been a long journey, especially started as a so-called pure modeler. And then, I evolved myself where, so-called from a pure modeler. Now I cannot call myself, either a modeler or an experimentalist. Rather, I feel I do both of them. And that is what I would like to, tell you through this presentation. Of course, I have, with me, of course, there are a lot of my colleagues who have worked with me. One is Professor Ballal, who has been always with me from the start. I joined IIT Bombay. And there are also Professor Sitaraman, there are also other people from Lilio University of Technology, and a lot of students from various steel industries, including, JSPL, JSW, Tata Steel, SR, all those people. So many of them have worked, and, some of those things are what I'm trying to present here. Of course, I have a lot of slides, but I can stop anytime because there are many case studies. And because of this, large number of years with large number of students, I also was fortunate enough to work in different areas. I mean, as far as iron and steel making is concerned, starting from pellets up to continuous casting. So that way, I will also try to run through to some extent, starting from the pellets, how, I have been involved in various process modeling as well as experiments, and my experience with those studies. Okay, so that is what, so that's why I have given title of my talk as process modeling in iron and steel making processes, some case studies. Just give me a second. Yeah. So before I, get into specific models, I just wanted to, share some thoughts on why models are important as far as, metallurgy is concerned, or materials process is concerned in a more generic fashion. If you look at our processes, they are very huge, highly heterogeneous, and many of them operate such high temperatures. So in that way, it is a great challenge for a modeler to, model the system. Of course, if you look at our curriculum, one of the complaints which we have been receiving, especially, regarding metallurgy curriculum is, it is not very quantitative compared to other engineering curriculum. This is, quite often a student's feedback also. But of course, one of the reasons is because our systems are very complex, so they are not that easy for us to quantify or put it in terms of numbers. But I think we have taken that as an excuse not to quantify, especially I can tell you in academic, curriculum, teaching, etc. This has been the problem, and I have been always, trying to address this problem in all my courses. And all my courses, I make sure that, the quantitative part comes always into the picture. Okay? This is one aspect. The other aspect I believe is, see, again, our systems are very complex, and it runs into different scales. So to study the system, we conduct some specific experiments. One particular aspect, maybe, you take a single iron ore pellet, do a reduction, RDI, or you find out the strength, or you take a coke, or you do some other, only flow, like that. We do very specific experiments. And then from there, we try to, extrapolate our understanding to the performance of the reactor or blast furnace, let me say. But then it is like, our old story, like four men and, blind men and an elephant. Somebody catches the trunk and says that the elephant is like a, pillar or something like that. Somebody touches the tail and says, no, elephant is like a rope. So to some extent, I can say that we have been like that. But model can actually help in systematically integrate all this knowledge, whether it is laboratory or plant, all those things in a nice way. So I see modeling as an opportunity to systematically integrate all the knowledge which we have gathered through different things, so that we can actually understand the real system. So that is the opportunity I see as far as modeling is concerned. Of course, let me also tell you that in some sense, whatever we do, it is all modeling. Whether it is in science, science also, what we do is we look at the system and then build an abstraction, some equation, whatever it is. And even an operator operates a blast furnace or a BOF. The operator also builds some kind of a model in his mind, in his or her mind, and then try to this is the way it will behave. So that way, we all modelers. It is not that modelers are somebody who is different. Even experiments we do is to build a model in some sense. We are making a conceptual model, or we describe the system. So that way, all our whatever we do is all modeling in some sense. Okay? So that's why there is a very famous chemical engineering professor, Rutherford Harris. So he talks about how conceptual progress, which is happening in our brain, or we make a model, and then of course the actual understanding about the system, and that improves the system itself. So it's a play between these two, is what he says. And this is one of the very important statement. He says it is impossible to design a good experiment without some theoretical vision, and more precise the theory, the more decisive the experiment can be. So if your theory is better, then you can actually do a more focused experiment. I will show you that some of these things through my presentation. Of course, he also comes with so-called maxims of modeling. Of course, he has many of them. Again, one of the things which nowadays many youngsters get into is we have now a lot of tools available, especially CFD tools, ANSYS Fluent or OpenFOAM or CFX, so many things. And we would like to simulate many, especially flow, heat transfer, all those things. And quite often for a beginner, it is like, you would like to put all the complexities which is involved in the system into that model when you develop the first one. So he says that is one of the worst ways of doing modeling. He says avoid rigor like plague. It only leads to rigor mortis. That means what he says is if you put too many things, then the model becomes so inflexible that it will not move. It will be like a dead body. That's what he means by rigor mortis. So this also one has to be careful. We have a lot of tools available, but again, when we do modeling, we have to do step by step. Okay. Anyway, these are, I thought, some of the things which I can share before I talk about modeling. Okay. And as far as the principle used in process modeling, which is, I will again say, that is what the whole science is about, is we have a conservation equation and constitutive equation. Conservation equations are, for example, conservation of mass, conservation of energy, conservation of species. These are, and then, constitutive relations are how a particular thing behaves. For example, we talk about constitutive relation. How does a steel behave when under tension, under stress? Similarly, how does an iron ore behave when you put it in CO atmosphere? So these are laboratory experiments which can be done, and from there we get so-called constitutive relation. So basically modeling, if you look at in a generic sense, it is combining this constitutive relations through conservation equation. So we use principles of thermodynamics, heat, mass, momentum transfer, reaction kinetics. And of course, we also use, this modeling doesn't mean it is only computational or mathematical models. We also make models, physical models, to understand things. So even information from there, all those things can be used. And let me also tell you that quite often there is a confusion between model and simulation. Most of us are actually, probably not modelers. We are all simulators, because already somebody has developed a model. We only use those models, to simulate something. So whatever we do in, Fluent or anything, I would like to call it more a simulation rather than a model. Other models, it needs much more in-depth understanding. Models can come only from experimentation. So that way, I will say, we quite often confuse between the term model and simulation. But anyway, so let me start from pelletization. So this is the work I did when I was a LKAB chair professor in the northern part of Sweden, where they have a lot of magnetite ore. And this is the, they have a induration, magnetite induration. So they make pellets, and they wanted to look at. And of course, I don't want to get into the details. Many of you will know what is a pellet indurator. Okay. So you make pellets and you would like to heat harden them. So what was the motivation for doing this problem was, if you look at the whole reactor, the induration reactor, there are two kinds of reactors, straight grate and the kin one. So if you look at, because this is actually a moving bed, and the pellets are stacked, it is in a bed like this. So the properties of the pellets can vary from top to bottom. Okay, because the temperature and the composition the pellet encounters, the gas composition the pellet encounters, is not going to be the same throughout the whole section of the bed. So then the quality of the pellet varies. Of course, this is even true for sinter also. The quality of the sinter varies from across the cross section because of the same reason. So, there are a lot of, they have already models for the reactor and all those things, but they don't have really a model which can predict the pellet quality. So hence I was asked, as a professor in that university, that can I look into this problem of how to address this quality? Can something tool be developed so that the quality can be assessed? That was their. So then I said, okay, we have to look it into a single pellet to understand, for different raw material mix, different grades, how do you go about, understanding the single pellet? Okay, so that's the way we started working on a single pellet. Of course, this was one PhD student who worked on it. So I'm presenting his work. So see, the thing is, of course, if you look at a single pellet, magnetite pellet, what we do with the hematite is different, and we have started doing that now at IIT Bombay. I have a PhD student who will be working on that. But on the magnetite pellet, the magnetite get oxidized, and then it also gets sintered. of course, the sintering can happen both for magnetite as well as the oxidized magnetite, which is the hematite. And interestingly, the sintering characteristics of the oxidized magnetite is different from the magnetite itself. Rather, what happens if you take a pellet, okay, it starts oxidizing from the outside, and then you have an unreacted core which is magnetite, and then what happens as temperature increases, this will sinter separately, this will sinter separately, and their sintering characteristics are different. Rather, magnetite sinters bit easily compared to hematite. So what will happen when you say sintering, means sintering leads to shrinking of the pellet. So what will happen, this unreacted magnetite, which is yet to get oxidized, that will start shrinking, and this one will not shrink that much. So then you will actually develop, one can develop a crack in the magnetite pellet inside. Rather, if you take those pellets, if you shake it, you will hear the sound like a copra. You will sometimes you will hear, you will get a duplex structure. So we wanted to understand these things. So the scientific way of doing things is, if you have such many phenomena which is happening, the scientific way of doing this thing is, you first look at one problem, understand this behavior. If you can isolate that particular thing, separately, without having the other things, and then use the modeling approach to integrate. This is what I was trying to tell you, that if you do very, once you understand, and then if you do a very focused experiments, then one can do a much better job than doing a blind experiment. So that's exactly what I have written. So study phenomena in isolation, seek the physics, that means through experiments, then you try to quantify. This is also very important. We need to quantify this, and then use the modeling principles to integrate, and then you can do the prediction. So what we did was, we know that sintering leads to a shrinkage. Okay. So we actually did a very simple experiment. It is called the heating microscope, which I think many of you may be aware. For example, if you want to find out ash fusion point, you take a small pillar, put it inside that heating microscope. So there is a light source, and then you get a shadow image. Okay, so that way you'll be able to capture how the size of this is changing. Okay, from there you can find out when it is going to soften, etc. So the same system we took it. Of course, we asked them to make it a bigger system, so that we can put a pellet which is of 10 to 12 centimeter mm size. So that way we put it inside the furnace, and then you heat it. There are pots, windows, and all those things. You have a light source and capture the image. And then as the temperature goes up, of course, the pellet will expand as well as it will get sintered. Okay. So this was, somewhere in 60s or 70s, some scientist has done it. Afterwards, I don't know why no one continued to use this. They were using another technique called dilatometer push rod, which has its own problem. I don't want to get into it. But we thought this is a much better system, so we worked on this one. And this is what, so we called, though it is a heating microscope, we call the name as optical dilatometer. So we have published at least 3 articles in Metallurgical Transactions on this particular methodology. So if you look at this is the temperature profile, one of the temperature profile which we there's a heating rate, then we maintain at a somewhere close to 1573, 1300 degrees Celsius, and then we cool it. Okay, and during that time the pellet expands because of thermal expansion, and then you can see that it starts shrinking because of sintering. Okay, So basically, it is a typical curve which we get from the optical dialectrometer. Of course, there are two phenomena which is happening. One is the expansion, the other is sintering. Actually, it can be very easily, one can eliminate the expansion, because if you plot with temperature, you will see that expansion is more or less linear with respect to temperature. So instead of time, I just plot with the temperature. You can see that, this is expansion and this is a contraction again during cooling. So I can very easily, eliminate that, and I can actually get what is the change in the pellet size only due to sintering. And that is what we used. And then we looked at, sintering is not something which is uncommon to a metallurgy community. Powder metallurgy, a lot of studies have been done on sintering. So they have done so many experiments. They use a parameter called sintering ratio. Again, I don't want to go into the details of it, but this can be derived out of that experiments. And we, for example, we conducted experiments for different temperatures, both for the magnetite as well as oxidized magnetite. Of course, when we oxidize the magnetite, we don't want sintering to happen. So what we did was we oxidized it very slowly. So that very slowly means at a low temperature where sintering will not occur. And we kept it for 2-3 days in the oxygen atmosphere so that the magnetite will completely get sintered. We checked it also, completely oxidized. And then that pellet, again, we conducted the sintering studies. So these are, the sintering ratio. And then again, we looked at powder metallurgy literature. There were actually very nice equations which describe how the kinetics of sintering can be, of course, those who are metallurgists, you would have studied, in powder metallurgy, there are different stages of sintering, the different mechanisms and all those things. But as far as iron ore sintering is concerned, we are only at the first stage because we want the pores to be there. So it's basically first stage of sintering, but in actual powder metallurgy, there are more stages. Okay. So there are all these equations are already developed. And the most striking thing was when we just put all that equation, we saw that all those experimental points beautifully, you see how nicely it is converged into one line, which clearly says that, this was the moment, we were so happy. We could see that actually, borrowing from our own friends in powder metallurgy, we could see that actually we can quantify sintering. Till now, no one was actually quantifying sintering in pellets. That was the, the sad part of it, because people did not look to quantify the sintering. And we could see that it was so beautifully coming in one line. Of course, then we analyzed, what is the activation energy? What are the reasons for it? Of course, academicians have their own, reasons to find. For example, Fe3O4 sinters much easily compared to Fe2O3. That is one of the reasons is Fe3O4 is a non-stoichiometric compound. So it has more, more defects in that, and hence diffusivity is higher. So it can actually sinter more easily compared to hematite. So some of these, insights were coming once we started doing this experiments. So, this was a very nice experiment, and we could actually quantify sintering. So that way, now what is the use for industry? Industry is basically, we have come out with some parameters, kinetic parameters. Actually, 3 parameters are there in this equation, and those 3 parameters actually puts you, gives the opportunity for you to know, okay, for example, if I add small amount of flux, how the sintering is going to change. You will be able to actually, if you have numbers, you can put them in order much better rather than saying, okay, this is better than that. We talk only without numbers, but with numbers, you can actually talk much better. So that way it gave them methodology. So now they are doing experiments, with adding their fluxes and all those things. But that is their own matter, because that quite often they keep it as a confidential matter. But the methodology was given to LKA. Of course, we also analyzed the microstructure and all those things. As I was telling you, this is the neck formation in sintering, which is powder metallurgy is well known. So we analyzed the microstructure and looking for bridges. So actually we had a collaboration with a computer science professor who works in image processing. And what we did, for example, this is the image of a single pellet, but actually this is not one image. This is several thousands of images stitched together, and we have obtained the whole picture. And from this picture, again looking at the bridging and all those things, image processing, one can also find out what is the sintering degree. So we saw that what we physically observed by shrinking, that can be actually correlated. That's what, see, this is optical dilatometer. This is actually from the microstructure. How beautifully these two can be correlated. Okay, so that way, macroscopic observation, how that can be correlated to a microscopic observation, that too in a quantitative fashion, is what actually we could establish through this analysis. And then we expanded this model because all the studies were conducted in isothermal conditions. So we expanded the model to non-isothermal conditions. Of course, these involve some techniques of modeling, but these are not very difficult things. These are used even many other places. For example, grain growth, when you do in runout table, if you want to predict the microstructure, there are equations available. So along the same line, we actually developed, and actually we did conduct experiments, non-isothermal experiment, to see whether our predictions are how good they are matching with the experiments. And you can see that these are some of the predictions, and the experimental, these are predictions, and you can see that it's a very nice, match between what we found experimentally and the models are. Okay, so that way, it's a judicious combination of experimentation, that too a focused experimentation can give much better information, and it can result in a quantitative, information. Then we, of course, this is one part where it is only sintering. Then we also went ahead with oxidation, and where we conducted TGA experiments. I don't want to go into the details, but we did all those studies also. But I just wanted to tell you, we looked at single particles of magnetite, which are there inside, in the pellet, and we looked at the microstructure. For example, this is the way the hematite grows, the needles of hematite actually coming in. Okay? So again, we used the principles from phase transformation to understand this, and there is something called Avrami equation. Some of you may be familiar, and actually we found that Avrami equation fits so well. Again, these are experimental observations, and we were fitting with Avrami equation. So that way we could actually describe the particle kinetics. That means actually we were going in different scales. One is the scale of the grains which are there in the pellet. Then the pellet where diffusion, and at the grain scale, this phase transformations, or this oxidation was happening. So again, we use the principles of diffusion, reaction kinetics, and conservation. All those things were used, and then we could actually develop models. So for example, this is the model versus experiments, and which is a very good match. And so that way we could quantitatively predict the oxidation, we could quantitatively predict the sintering. So that way we studied the phenomena in isolation. Now we can combine these two, because sintering affects the oxidation, because once the sintering happens, the voids get closed, so the gas cannot reach. And of course, depending on whether it is magnetite or oxidized magnetite, the sintering was going to change. So oxidation is going to get affected by sintering. So hence now, once we know in isolation, we can use the principles of modeling to integrate. And that's what we did. And that's why this, and of course there is an associated heat transfer. So now we use the principle of modeling, and actually we can predict. If you look at very carefully here, this is the oxidation progresses, how it is progressing. Okay, and you can also see the pellet shrinking. If you look at, here the pellet you look at, and by the time it has come here, it has already shrunk. So now basically, so we have developed what is known as a, we call it SPIM, single particle induration model. So now LKAB is using this SPIM model in their actual reactor model. So that way they can assess, or they can at least predict the quality of the pellets across the cross section. Of course, they have to conduct experiments, because whenever they have a new mix, they have to conduct experiments to find out the kinetic parameters. Once they find out the kinetic parameters, plug in those values into the model, then put into the reactor scale model. That way they'll be able to assess, for example, how much shrinkage has happened, what is the oxidation front mood. From there, they'll be able to assess the quality of the pellet. So some kind of quantitative information they are able to get from this particular model. Okay. So that is as far as the LKAB is concerned. I was not involved in the reactor scale model. Then I came back to IIT Bombay. Then, here when I came, I was very much interested in pellets. And then, we have always students coming from industry, so who are interested in various iron and steel making process. So I got of the industries who wanted to look at the temperature profile in a straight grade induration furnace. Of course, this is not a magnetite induration, but it's a hematite induration furnace. So then, those who know pellet induration, there are different. There is a drying zone. There is updraft, a downdraft drying zone. So this is the pellet bed which is moving. So schematically, this is shown the pellet bed. So there is a preheating zone, there is a firing zone, after firing. So different zones are there. So we wanted to know how the temperature profile is going to develop within that bed as it moves. Okay, that is what the industry was also interested in knowing it. So again, I don't want to get into the details of equation. I thought that is not the purpose. But these are again heat transfer equation, conservation equations, equation for evaporations, etc. Again, I'm not going into the details of the equation, but that's what I was trying to say. So these are the inputs, and these are the different models which are available. These are well-known models. So in that way, I'm not using anything which is my own. It is all already there in the literature. People have done different experiments of drying and all those things. So all those things are put together. So it's again an integration which we are trying to do. And from there, we can predict how the bed temperature, what is the pressure profile, and all those things we can predict. And for example, this gives you the temperature profile. Okay. So because of this, the hot gas come from the top, the pellets on the top, they spend more time at high temperature compared to the pellets at the bottom, which spend relatively less time on the high temperature time, or the residence time is different for these pellets and these pellets. Okay, so accordingly, the quality, this is what I was telling, the quality is going to be different for a pellet here and pellet here. Okay, so the most interesting thing we really got excited was, which I am not able to show, but I can only tell you, is for example, this is the temperature profile for different pellets sitting at the top versus pellets sitting at the middle and pellets sitting at the bottom. So that means as it moves, pellet at the top, how does it experience a temperature? Pellet at the middle and pellet at the bottom. So that's the temperature profile. Then in industry, they use a technique called thermocar. What they do is, in one of the pellet cars, okay, they put a thermocouple, means thermocouple, not only thermocouple, also the data logger. And remember, this whole system has to move through the whole induration furnace. So this is a very costly thing because they have to make sure that the data logger is well cooled. Otherwise, at these temperatures, it will not work. So that's a sophisticated system with a lot of cooling arrangement and all those things. So that means in one of the cars, they put in this thermocouple plus the data logger system, and they put into the car, and by the time the car comes out, the data logger can be taken out and see what is the temperature profile. Okay, so this one experiment cost around 60 lakhs. Okay, so plants sometimes do these kinds of experiments to understand how the temperature profile inside the furnace is. Okay, for reasons of confidentiality, I'm not able to show those points, but I can tell you that whatever we did, we also didn't, without even much tuning, the temperature profile was matching with one of these profiles so nicely. So what I'm trying to tell you is, now we have established the confidence that okay, model can predict the actual plant temperature data. So now tomorrow, I change some of the parameters, I change the gas flow rate, I change the gas temperature, or I change the speed of the production rate, how those things can affect, by a simple model. I mean, we could, once we establish that confidence, it can be used, often, and it can save a lot of money, because doing one experiments in such large scale can be quite expensive. Okay, so we were quite excited to see that it matched quite well with the experiments. That too at the plant level experiments. Okay, so that is as far as pellets are concerned. How much time I have? Hello?
Sir.
Yeah.
Yes, sir.
How much time I have?
Still half an hour is there, sir.
Still half an hour? Okay,
Yes,
I'm
yes,
halfway. Okay, sorry. Yeah. So now let me go to the next, which is blast furnace. Blast furnace has been my love. The moment I wanted to do even my PhD in blast furnace, but unfortunately when I was during my PhD, there were a lot of issues with cupolas. Maybe some of you may not know. At that time, a lot of cupolas were closed because of pollution and all those things. So my supervisor asked me to work on cupola. So probably that is the last PhD work in cupola probably in the world. Okay. So I worked with Professor Lahiri, again a pioneer in modeling. So at the Indian Institute of Science. So, that way I wanted to work in blast furnace, but I started with cupola, but my love for blast furnace did not leave at all. And as soon as I joined IIT Bombay, I started working on blast furnace. And let me tell you, I continue to work even now on blast furnace. Blast furnace is such a complex reactor. It really a challenge for a modeler. It has so much opportunities as far as the modeling is concerned. And if you look at, of course, blast furnace for such complex system, models can be developed at different rigor. There are so-called simple model, which I call it 0D for the time being. Of course, you can have a one-dimensional model, you can have a two-dimensional model, you can have a three-dimensional model. All these models have their own purpose and their own utility. It is not that the 3D model is better than a 2D model or a 0D model. Rather, 0D model is something which can be used very regularly with an operation to understand how the parameters, how good the operations are. All those things can be analyzed. But 3D is something, which an operator can never touch it. It should be done for, some understanding some new way of doing things, or, how design aspects. Some of these things maybe 3D can be useful. So they have their own purpose. So one should not say that the one is better than the other, etc. They have their own utilities. So one has to develop a different rigor, and that needs to be done. And fortunately, I I could, do 0D, 1D as well as 2D. Okay? And not really a three-dimensional blast furnace model, but up to 2 dimensions. Okay? So I will tell you my journey. This is again last 20 years I have been doing. Okay? So when I joined IIT Bombay, there was a large national project where NML, Tata Steel and SAIL, they were involved, and they were doing actually, they were putting probes into the blast furnace, vertical probes, which will descend from the top to the bottom, and then as it is, then it will take the readings and it could find out the temperature and all those things. And then we at IIT Bombay, we were developing the models for the blast furnace. Okay. So let me start with the 0D model. I don't know how many of you are aware, means one of the great books to study blast furnace, to understand blast furnace is, at least from my personal recommendation, is there is a book by PC and Davenport. It's a beautifully written book without any ambiguities regarding blast furnace. So, if you look at blast furnace has been challenged by many reactors. Okay, but let me tell you, blast furnace has stood, the challenge of time, and let me tell you that even now, blast furnace will remain as the main iron producing unit, though people are trying different ideas, and there are reasons for it. See, blast furnace, one of the words we use to describe blast furnace is chemically and thermally efficient reactor. These are the two words which describe blast furnace. Why these words are used for a particular reason. See, why thermally efficient is, gas is going from top to bottom. The solids are coming from gases are going from bottom to top, and the solids are coming from top to bottom. Now, when you have such a flow, the heat transfer is maximum when both phases reach the same temperature, because after that, it cannot transfer any more heat. Both of them reach the same temperature, both gas and solid reach same temperature, it cannot transfer any more heat. In blast furnace, such a region exists, which is called the thermal reserve zone, where both the gas temperature and the solid temperature reach the same. That way, it is thermally efficient reactor. Why it is chemically efficient reactor is, again, see, we know that to a reaction to occur, there should be a driving force. We call it free energy, etc. Okay. For example, if I take wustite, which is FeO, if I take 1 mole of wustite and if I make it react with 1 mole of CO, I will not get 1 mole of iron as per stoichiometry. You may think you will get, but that is not possible. Thermodynamics says, experiment says, you need excess of CO. That is, you need to produce 1 mole of iron, you need actually 3.3 moles of carbon monoxide, not 1 mole, because based on second law of thermodynamics of equilibrium. So that means that is the maximum extent to which reaction can happen. So you need more than that. So in blast furnace, there is a zone called chemical reserve zone. Again, it is part of the thermal reserve zone, top part, where the reaction reaches equilibrium. Reaction reaches equilibrium means the reaction has reacted to the maximum extent the thermodynamics permits. You cannot violate that. So that way, blast furnace is also chemically efficient because it permits the reaction to happen to the maximum extent the thermodynamic permits. Okay. So based on this idea, Rist is the one who started, but that's a beautiful concept, and even now it can be, it is used world over in analyzing blast furnace performance, where one can actually divide the blast furnace as 2 reactors, one on the top, one at the bottom. And in this zone, we know what is the temperature, we know what is the composition, because equilibrium is there. Okay. So based on that, actually one can find out, once you have a, this is the raw material I am using, this is the coke I am putting, this is the PCA I am injecting, this is the, other than PCA, I put hydrocarbon, I put natural gas, all those things. then what is the minimum coke which is required? That means no blast furnace can operate less than this coke for other conditions being fixed. Means blast temperature, what is the pulverized coal injection, all those things are fixed, and corresponding to that coke rate, what is the blast rate. Okay? It's a beautiful, very simple model. This is what the PC Davenport, that whole book very nicely tells about. Okay, so I don't want to again go into the model details, but I can tell you based on this. So basically, the model contains three things. One is oxygen balance. For example, oxygen coming from iron plus oxygen coming from the blast, water vapor, whatever you add, all those things should be equal to the oxygen which is going out through the gas. That's an oxygen balance. There is a carbon balance and there is a heat balance. And based on that, actually you can draw what is known as an operating line. Okay. So this is, this is actually the oxygen, and this is the oxygen by carbon, which is in the gas. So this is the oxygen which we are giving through the blast. This is the oxygen which is coming from the ore, and this is the oxygen which is going out through the carbon. And you can very beautifully draw a line. Okay, and you can actually draw this line. I'm not going into again details, but telling you such a simple model. We teach it in the classroom. Okay, students all do it, and we can actually, this is the theoretical line, and then based on your top gas composition, what is the oxygen you put in, you can actually draw another line. Okay, and the deviation from this line will give you what is the efficiency of the blast furnace. Okay, how efficient? I can tell you, blast furnace can operate 95-96% efficient, almost close to ideal condition. Now, again, if I look at many industries, they compare their blast furnace fuel rate or coke rate and all those things. They compare it with some of the furnaces abroad. Okay? Actually, this is a very wrong way of comparing. It's like comparing apples and oranges, because the fuel rate depends on what is the raw material which you charge. Our iron ore contains a lot of alumina. To take care of alumina, we add extra quartz. And to take care of extra quartz, we need to add additional lime. So our slag rates are much more than what is there in abroad, some of the furnaces outside. So, straight away comparing, okay, our coke rates are much more than their coke rate. No, we need to reach there. I think that is the wrong way of doing things. We need to, use these kinds of models, because you cannot get a coke rate better than what this model predicts, because you cannot violate thermodynamics. So your benchmarking should be using this rather than just benchmarking with somebody else's coke rate, because they get much better ore, so they can do it. For example, in Sweden, they have 100% pellet operation in one of the SSAB furnace. They have been doing it for 40-50 years. They say almost there is no cozy zone at all. So our operations are so different. So one has to understand that. And then, so this model is something which, I know that ArcelorMittal, for example, they use it regularly. To some extent, Tata Steel use it, but I don't think other plants are still using effectively. This is not, new model. This is as old as, 40-50 years old. That's what I'm trying to tell. But still, and it's a very simple model, but still we are not using it, and we can do many things with that. Okay? For example, this is one such, this is the ideal line, this is the operating line. Okay, and you can also include not only carbon but also hydrogen, because nowadays we are very much interested in using hydrogen, because we want to bring down the emission level, carbon emission level. So we would like to put, hydrogen containing things. So for example, India probably may start using more natural gas. I don't know. These are the possibilities, because we are thinking of some natural gas terminal, on the eastern coast and the western coast. From there, the natural gas will be pumped. These are some of the ideas which has been floated by our Prime Minister, and I know some of the large companies are interested in it. For example, I myself is in working with ExxonMobil, which is one of the largest supplier of natural gas. So they are actually interested in finding out what is the maximum amount of natural gas which can be injected into the blast furnace under Indian condition, whatever iron ore, coke, PCI we get, what is the maximum amount. Let me tell you, I can analyze all those things using this particular simple model. Okay, what is the maximum amount and how much carbon emission levels are going to come down? All those things can be analyzed. So I'm working on it. Again, I'm not allowed to show some of those results, but I'm trying to tell you it's a beautiful model, very elegant model, which I think all the plants should be using it to look at their blast furnace performance on a regular basis. Okay? So that way, this simple model is it can use to benchmark blast furnace efficiency, explore new possibilities, as I told you, and even you can look at top gas recycling. Okay? And let me also tell you that one of the ideas which IIT Bombay, Professor Ballal, he has been telling is, there are some experiments which was done in Europe to recycle the gas back, because it contains 20% CO, 20% CO2. So remove the CO2 and then put back the CO into the furnace so that your coke rate carbon rate can come down. So unfortunately, this is the reason I went to the north of Sweden, because they have an experimental blast furnace. They have installed this recycling facility there. So I could, interact with those people there, and it was such a wonderful experience. Anyway, so we have to work on new ideas also ourselves. Okay, especially India has become the second largest steel producer. So we have also signed the Paris Treaty, where we'll bring down I forgot 2005 levels, some 30% of that by 2025 or 2030, I think. So we have also such commitments we have made. So if you want to do all those things, we have to bring down our carbon emissions and we have to try out new techniques. So one of the ideas which we have been advocating, we are working on it, this is an idea, is to remove the gas from the so-called the chemical reserve zone, which I was describing. Why, I'll tell you, is one of the problems which we have in Indian blast furnace is alkali problem. Okay? So you know that the alkali, what happens at the bottom of the furnace, it is gas. So it cannot go out with the slag very easily. And at the top, by the time it reaches, it condenses. So it cannot go out with the gas at the top. It cannot come out with the slag at the bottom because it is gas. And there it is, it should be gas, but it is solid. So it keeps recirculating inside, and that's a problem. Okay? And this affects the blast furnace performance. Many of the blast furnace irregularities are because of alkali and zinc. That's the other culprit we have. Because of that only, we have a lot of problems. So if you can take out the gas from the somewhere in the middle, that's what, some 3 to 4 meters from the top, the temperature will be high enough and these alkalis will be in gas phase. And then you cool it and recycle back. That may be a better idea, and we'll be able to probably, push our furnace much better, because, alkali, a lot of alkalis can be removed if you take out the gas. If you take it from the top, it is already cooled, so still alkali will be inside. So that is what is our idea, where we have been telling, we are working on some of the calculations, etc. Of course, these are ideas, but needs a lot of experimentation. So I have been suggesting also, we need to have an experimental small blast furnace. Like, Sweden has one, which a lot of European use. There are also experimental blast furnace, which is there in Japan. Of course, it is not that we cannot have an experimental blast furnace. We have a lot of mini blast furnaces in the secondary, the sector, the small furnaces. Once you instrument those furnaces, it is possible to conduct these experiments and, test some of these ideas, and that can result in innovation. See, just ideas coming out is not sufficient, but that needs to be tested. That testing needs a lot of money, a lot of, because especially these kinds of reactors, somebody has to put in money and try out these things. Okay? Then only it is possible to come out with technology there's some, academician sitting in an institute and, giving ideas and trying out things on the paper is not sufficient. That is only a beginning. And there is one needs to have further people working on it to make it actually a process. So it takes so much time. Okay? And time, effort, as well as money. So we should be ready to do that. Then only innovations, at least in iron and steel, can come. Okay. Then my journey to blast furnace simulation continued. I had a PhD student who worked completely, he wrote all the codes to develop a 2D model. Let me tell you that when it comes to blast furnace, you cannot use all these commercial codes. Typically, it's difficult. Let me say, we cannot use, I should not claim, but it's very difficult to use because, so many reactions happen. There is a melting, so many things happen. And all this flexibility is difficult. And not only that, if you look at flow of liquid steel through a tundish or anything like that, there, hello? Yeah, how much time I have?
Yes, sir. Please go ahead, sir. No issue. Please go ahead.
Yeah, you let me know. You have to tell me stop, I will stop. Okay? Because I have only reached halfway as far as my slides are concerned.
So, no issue, sir. Please go ahead.
Yeah. So, what I was telling was, for example, I'm looking at flow in a tundish. Okay? First, we look at flow, then heat transfer. Okay? The heat transfer doesn't affect the flow very much. Okay? I will not say it will not affect. It can affect, but very low. But on the other hand, blast furnace, it is not that way. You put in, 1 ton of gas, you get 2 tons of gas at the top. That means there is so much exchange of, species, oxygen and all those carbon, etc., from gas to solid to gas phase. So that way, the flow equations, the reaction equation, the temperature, all those things are highly intercoupled. Okay, so that's why this intercoupling is shown here. So that way, the commercial softwares are not that easy to. So that's why we decided to write our own codes. But it was a mammoth exercise. Of course, let me tell you again, Europeans are one, and Japanese are one. And you look at Japanese one, they started writing, Japanese are pioneers in blast furnace because they quenched, the actual blast furnace, 7, 8 of them somewhere in 70s. And that is what revolutionized. Remember, blast furnace, quenching blast furnace, actual blast furnace. Okay. 7, 8 of them in 70s, and that too the one which are working good and the one which are working bad, so that they will know what is good and what is bad. That's something great about Japanese, and that is what revolutionized the understanding of blast furnace. Okay, and from that time onward, they started developing models for blast furnace, and they had a committee, joint. I forgot the iron and steel. Some committee is there. They have come out with a book also. And let me tell you that they used to meet apparently every 2 months, once they used to meet. And they met for 20 years. People died, though some of the committee members, they passed away, they retired. Without break, they met. And that is a commitment. And with those commitment and all those things, they came out with a model which is called Bright. Okay. And Europeans also, there are some models which are available. But in India, there was not serious efforts. Of course, my own supervisor had done some work on blast furnace modeling, but there were not serious efforts unless we came into IIT Bombay. As I told you, that national effort, and as a part of that, we started developing the model. Of course, we developed using our own MTech students and PhD students and our own codes. We did not use any commercial codes. It was okay, but we couldn't make a robust code which can be actually run by somebody else and all those things. So I was not satisfied, though, but it developed a lot of understanding. We struggled so much and all those things. Then an opportunity came because Tata Steel is well aware of all these developments. They have been interacting with us very closely. So then they came out. I'm not going into the details. We developed 1D. So it was 0D, 1D, then we went to 2D. So that was our journey. As I told you, you develop models in steps, not you don't jump into the straight away to a rigorous. So so Tata Steel came to us, and then, we said at that time, already there is another open source software called OpenFOAM. I don't know how many of you are aware, which is an open source, which has a completely different philosophy where all the codes are available. It's a CFD software, but it's very different from, the commercial ones, where all the codes are available and the flexibility it offers is so high. So then there was a company in Pune called Tridiagonal Solutions, which they were experts in OpenFOAM. So we had actually a tri-party, collaboration, where we had the vast experience of, so many years of working in blast furnace modeling. So all equations, what are the difficulties, all those things were with us. Tata Steel has, experience of all operation, all those things. And many of my students who worked in blast furnace, they are all in Tata Steel, many of them. So they were, and then Tridiagonal Solution. And I can tell you, we worked very hard for 18 to 19 months, and that resulted, basically, when we have such tasks, we have to respect each other's expertise. This is something, again, this collaboration, I believe in India, we need to learn from, many other countries where, the industry, the academicians or some other expertise, they all have to come together and work towards a common task. And it is not, just one person, one organization. It cannot be that way. Again, I can tell you based on my experience in Sweden, where when they design projects, of course, some projects are academic in nature, but still in those projects, there will be always, people sitting from industry on a regular basis for reviews and all those things. They are also part, they will contribute to the project. And there are other projects, a continuation of, you suppose this project becomes successful, what is the next stage to be done? That also they plan. And in those projects, the leadership is taken by the industry, but the academicians are always part of it, so that there is a nice, smooth transfer of, knowledge or whatever, information or whatever it is. So that is the way they execute projects. Okay. So I think, again, if I look at least my experience here, it has been I will not say that it was that smooth as, when I worked for LKAB, when I, as I was telling you, other projects also, when I worked, the experience I got from Sweden, it was quite a learning experience, and that we need to integrate here. And one of such experience was this particular project where, there was somebody who is expert in CFD. They have done so many other work, but they didn't know blast furnace. But he had a lot of experience in blast furnace modeling and all those things. So it was actually a very good combination. It was a pleasure to work, and we could come out with, for the first time, a 2D complete model for blast furnace, which we call it as BLASTIM. This is named by Tata Steel. Okay. So, it can give a lot of things. These are some of the things. For example, it has, once you have a charging model from the rotating chute, how the burden is going to descend. Okay. Then, we even compared with the plant data and all those things. It was a good comparison. Again, I'm not going into the details of modeling. It's a very complex modeling. A lot of things are involved: reaction kinetics, heat transfer, flow, all those things are involved, melting, liquid flow, all those things are involved. And you can see that it can predict, actually, that is what I wanted, is to prediction of the Cozy zone in the blast furnace, which, which is very difficult to know for an operator. Of course, to some extent, they try to get it from, the stave coolers, from the heat flux data. They try to assess where is the location of the Cozy zone. But this is going to affect the quality of the hot metal, because, if how much time the metal spends below this corrosive zone is going to determine what is the silicon content, all those things. And blast furnace performance is going to greatly get affected by this. And that also depends on what is the charging, burden distribution and all those things. So we could actually come out, it can predict now for different operating parameters. Suppose I increase the blast rate, will the corrosive zone move up? Will it move down? How much it will move down? Many of those things at least can be, you can get the direction, you can get an estimate. Let me tell you that this model cannot be used by an operating person. This is for a process engineer. This is again something which our community or our plants have to think, where operator has to be different, a process engineer has to be somebody different, who comes out looking at the analysis of the process, both from the theoretical angle as well as from the actual operation, come out with SOPs, standard operating practices. You fine tune the standard operating practices. As far as I know, even now, many of our industries, of course, they do change standard operating practices to some extent, but mostly these are given by whoever is the technology provider. Beyond that, we don't do much. And that too, whatever we do, it is based on so-called experience rather than, a systematic analysis through different inputs. Modeling is one input. I'm not saying that only this should be used, but this is one such input. Along with that, statistical analysis. So there should be a team, process engineering team, which should continuously work to, fine tune the SOPs, come out with new SOPs, etc. We need such a team. And that is where actually real engineers who with analysis will be quite useful. So I've been telling this to the plant that you need such a group, a process engineering group, so that you can come out with SOPs. And for them, these models can be useful, not for an operator. The 0D model, which I was telling earlier, risk model, that can be useful to operator. That's why I said, depending on the objective, it will change. Okay. So this can predict many other things, what is the wall pressure profile, and what is the temperature, what is the liquid temperature, fraction, reduction, all those profiles it can be predicted. Okay. So now, of course, the model is with Tata Steel. They are the owners of the model. I was only a collaborator. Okay. So maybe I can go to one more case. Do you have time?
Yes, sir. Please, by 12 o'clock, you just
12 o'clock. Okay. Okay, fine. Yeah. No, I can stop for discussion also. It is up to you. As I told you, I can stop at any time. So, okay, let me spend maybe another 5 minutes on this. This is, something interesting which we are doing experiments also. Very fundamental experiments. So these are far away from the industry, but still it has a lot of relevance. Okay. See, one of the difficulties in modeling in blast furnace is below the corrosive zone, where you have coke is there, you have liquid, and liquid means you have metal, you have slag, and you have gas going up. And industries want to push the production. Okay. See, there is always a once you try to increase the production, your efficiency will come down, your coke rate will go up. That is true for all systems. When you want to do more faster, then your efficiency will go down. It is true for all systems. Okay. But there is also a difficulty in pushing the furnace beyond a particular point, because what happens, the liquid is coming down and the gas is going up. And as the more and more, as you increase the production, the more and more liquid will be produced and the gas is going up. So it will offer a resistance because more liquid is coming down. So then the pressure drop will increase. Okay. So then the operator will say, no, the furnace is not taking the wind. Okay. So beyond a particular point, you start getting all kinds of problems. So there is a, this particular zone, especially liquid, solid, and gas going up, that particular zone has an issue. This is one aspect of it. Okay? That's why it's called the dripping zone. So we wanted to, in modeling also, we had a lot of difficulty. We have to do a lot of tuning in this particular drifting zone. So we wanted to look at this zone in a more careful, fundamental manner. Okay. And there is also something very nice, this is done by my student Snigdha Ghosh. She'll be soon faculty in one of the IITs. So let me tell you that these are very nice experiments which are done by chemical engineers long time back. You take a bed of particles and then you pass the gas from the bottom, you spray liquid from the top, you allow uniformly. Now what happens as you keep increasing the gas flow, of course liquid is also trying to come down. At one point the liquid cannot fall down, it will flood the area. Okay, this is one aspect, this is called flooding. Okay. Very simple, this can be done even in the laboratory with water and pebbles and just allowing the gas to go up. There is also another interesting thing. Suppose I have I have liquid coming here and the gas is going from the bottom. I suddenly stop the gas flow as well as liquid flow. Now what will happen? The liquid will drain, but all the liquid will not drain, because between the particles, because of surface tension, there will be some liquid which will remain between the particles. Okay, this is called static holdup in chemical engineering, and blast furnace also we call it static holdup. Why is it important? It is important in blast furnace. I'll tell you why. Because in blast furnace, the slag is much more viscous and its interfacial properties are different. Actually, most of the slag reaches the bottom through static holdup. That means as the coke moves down, with the coke, the slag moves. Okay, because it doesn't have a relative velocity between the coke and the slag. Okay, but on the other hand, the liquid metal, which has very less viscosity and interfacial properties are different, it will very fast, it will flow. So the way the slag flow is different from the way the metal flow. Okay, so we wanted to understand this, and people have not really understood these things, including chemical engineers. So then we said, okay, let us look at it from, so this is from an academician's perspective, please understand that. Okay, so we thought, okay, to understand that complex system, we need to understand how much a liquid can be held between two balls. Okay, so this is an experimental system which was designed where I have two balls. Of course, these are alignment and all those things are issue, and then use a micro syringe and find out, you keep injecting small amount of liquid will stay there. You find out what is the maximum amount of liquid which can be held between these two spheres. Okay, and that is what we did. Okay, and you can do not only that, now you can change the orientation. You can rotate this and you can find out this orientation, what will be the liquid, this orientation, what is the liquid, all those, and you can do these experiments and we can find out. So this we can do only it's easy to do with water and balls, glass balls or some, wax coated balls, all those things you can do. It is very difficult to do these experiments at high temperature using, slag and graphite balls. It's much more difficult, but we can again use the techniques of mathematical modeling to see what will happen in case of metal and slag. So what we did, so these are some of the experiments. I don't want to again go into the details, but you can see that 200 ml, 250 ml, 300 microliters, sorry. And you can see that, somewhere here it starts coming out. So there are a lot of interesting phenomena. Okay. So we also did a mathematical modeling. Again, this was a tough modeling exercise where, you start with the surface, that means the liquid film, and then you do so-called energy minimization. There is an interfacial energy, there is a contact angle. So there are gravity acting, all those things. So you can do what is known as a minimization of energy. What we do is we randomly change one node, find out the area, change an area, like that you do iteratively. So it needs a lot of parallel processing, computationally very intensely one. So we did that, we did a lot of parallel computation, and I can tell you this is one experiment. Okay, inclined, I don't know what is the angle. Okay, 30 degrees, yeah, and you can see the water film. Okay, and you see this is simulated using the principles, surface tension and contact angle. These are the only values we use, and you see how good the fit is from the simulation as well as the experiment. Both are actually exactly matching. Okay, that means now we know from fundamentals how to predict. So now, of course, this can be extended if I change now the surface tension, for metal, slag, all those things can be done. Okay, so again, depending on, if the contact angle is not good, then it is going to form a film which is not like this, it is going to flow like this. So many things are, many fundamental things can be explored, but I'm just telling you how the techniques of mathematical modeling can be used. And then we did experiments at different orientation. This is vertical, then you change some other, 10-degree angle, 30-degree angle, even up to horizontal. And we measured experimentally what is the, the hold up. You can measure it, and you can see that, whatever we predict using the model is very well matching with the what we found out experimentally. Okay. Of course, there are more complex issues. What will happen in the actual hold up will be less than that in the packed bed, because now this can be extended to packed bed, because packed bed can be thought of, distribution of these different orientation. Okay, so we can extend it to the packed bed and find out the hold up. But there is a problem here. What happens is, in actual packed bed, once the liquid forms, it will drip out. When it drip out, some part will pull back and some part will fall down. So actual hold up will be, it will not be maximum. It will be somewhere in between the maximum and what was pulled back and remained. So actual, hold up will be less than, because this is a maximum hold up. If no liquid, really falls down, if it all stays there, that is all this is. But actual one will be actually between, this is the lowest. So somewhere in between is, and that depends on, if you shake the bed, it will be different. But we could come out by saying that, what will be the hold up and what is the fundamental principles which govern this hold up. Okay, so this will be soon published again in a metallurgical transaction. It is accepted but not yet published, so it will be soon coming. So this is a PhD work by one of my students. Okay. So I think I will stop here, because I have again on some more studies. Just to tell you, this is done by one of our Chinese students. I did it with Professor Sitaraman, where she was trying to inject CO2 into iron chromium carbon melt. Okay, she did a lot of experiments and induction furnace, very tough experiments. Tough means it's dangerous experiments, injecting oxygen and CO2, into the liquid steel in a laboratory setup, but still it can be dangerous. So then the idea was, is it possible to, we want to oxidize, carbon in preference to chromium, and that's a problem with stainless steel making. So using CO2 can be reduce the chromium oxidation. That was the whole idea. So again, we did experiments, we did modeling, okay, and there are a lot of modeling issues involved, how a bubble travels and how the chromium travels around it and all those things. Again, I'm not going into the details, but what I wanted to see, this is actually carbon, this is chromium. Okay, this is the so-called the equilibrium line. Okay, we will never reach the equilibrium line. It's very difficult. But if you look at, if I put pure oxygen, so this is chromium. Okay, somewhere around 1.3 or so, the chromium starts oxidizing. Though thermodynamically it should start oxidizing, somewhere around 0.8 or so. But it will start oxidizing much early. That means your chromium loss will be high. So this is for oxygen. This is for a mixture of oxygen and carbon dioxide. This is for carbon dioxide. Yeah, hello? Hello. Yeah. So you can see that,
कौन दिया ऐसे बताइए पूछिए हमको नहीं पता है.
Okay. So these kinds of things can be, done. And I can tell you, this student, she did it almost 12 years back. She was in IIT Bombay also, but she was primarily in Stockholm, and she spent here 3-4 years. Now she is a professor in USTB, University of Science and Technology, Beijing. And they have gone ahead with these trials so much. Now they are injecting CO2 into their BOF. Okay, their basic oxygen furnace, they are injecting CO2, and they are getting, even for phosphorus removal, they are getting much better results. So now people are talking about injecting CO2 so that, better phosphorus removal can be done. And also they are now building a huge pilot plant where for low carbon ferrochrome, to production of low carbon ferrochrome, they are having a CO2 kind of an injector. They are having a reactor they are designing. It is at the pilot scale. So again, what I'm trying to say is, of course, these are some 12-13 years back, the laboratory ideas with some modeling. But now these things are, again, Chinese are able to scale it up, and they are able to come out with ideas. And some of these things, how nicely they are able to take it. And it is also important that we also work together, academicians, industry, technologists, or whatever, all those people. And we have to put money and effort wherever, and we have to work for 10-12 years. Then only we will start getting technology. It is not going to come in 1 year or so. So we need to have such long-term plans if we want to be really innovative. It is not going to happen just like that. Okay. So with that, let me just end my presentation. I have many more slides. Just a concluding remark by saying that neither modeling alone. We have a habit of, stamping someone, oh, he's a modeler, he's an experimentalist. I don't think it is, he's an operator. All those things doesn't serve the purpose. We are all actually do modeling as well as experiments. So that way, neither modeling alone, because if you do only modeling, it is building models in air, nothing else. Nor performing experiments without quantitative focus. Just, experiments to perform, okay, it increases, it decreases, all those things. Blind experimentation without quantification, without looking more deeper. So you need a, quantitative outlook, and through that you conduct experiment that will be more fruitful. So neither modeling alone nor performing experiment without quantitative focus will be a scientifically fruitful exercise. It is a judicious combination of both is what is required. That is what at least my 22-23 years of experience has taught me. Thank you very much for your